Welcome you in the lecture series of Basics of Communication Engineering. It is 24th lecture of this series. In previous lecture, we have discussed about differential pulse code modulation, delta modulation and adaptive delta modulation. In this lecture, I would like to discuss about multiplexing of signals, and the outline of this lecture are: why multiplexing, basic concept of multiplexing, categories of multiplexing, where we will discuss about frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. And time division multiplexing is of two types: synchronous TDM and asynchronous TDM. After this, we will discuss about digital signal services and comparison of FDM and TDM system. And in the objective of this lecture, you will able to explain the need for multiplexing and distinguish between multiplexing technique and the key features of TDM, FDM and WDM, and distinguish between synchronous and asynchronous TDM, and also you will able to explain PCM TDM system. Now we start with why multiplexing. Multiplexing is a technique that allows the simultaneous transmission of multiple signals across a single data link. Here you can see the n input channels are multiplexed into one output, and this composite signal is transmitted through a single transmission line. So n channels are transmitted through a single line. This is multiplexing. And at the receiver, we will do the inverse operation, means this composite signal is decomposed into n different channels. So now answer why multiplexing: because the cost of maintenance of high bandwidth link and low bandwidth link is same. So telephone companies have developed a elaborate scheme for multiplexing many lines into single physical line, and the communication media usually have much higher bandwidth. For example, we use coaxial cable, optical fiber, microwave. On the other hand, individual users have lesser data to send, and as a consequence, two communicative stations do not utilize the full capacity of the data link. So when the bandwidth of the medium is greater than the individual signal to be transmitted, a medium can be shared by many more than one signals using multiplexing. And essentially what we are trying to do here, we are trying to share the channel capacity or bandwidth of a particular medium by signals of several users. Now let us see the basic concept of multiplexing. What we do, we use a device known as multiplexer, which combines signals from n channels and send through one communication link. And at the other end, what we are doing, there is a demultiplexer performing the reverse operation. It is separating out the signals coming through one communication link, and it is sending them to n different channels, say 1 to n. Here this is 1 to n, and this is the basic operation. So the multiplexer and demultiplexer does the operation of combining and separating out. For multiplexing, we can use analog or digital signal. In analog, we generate a signal by using FDM and WDM technology, and the TDM is done using digital signaling. And TDM is of two types: synchronous TDM and asynchronous TDM. So first of all, we will discuss about the frequency division multiplexing. Analog multiplexing technique. It is applicable when the bandwidth of the link is greater than the combined bandwidth of the signal to be transmitted. It is an analog multiplexing technique that combines analog signal. Here n channels 1 to n are multiplexed and sent simultaneously through the same medium, and the signals combined from different channels are frequency translated to different frequency. At the other end, the demultiplexer will receive the signals, and they will separate out the channel using suitable device. So here you can see all are sent in parallel as far as time is considered, And if you look from the time point of view, all the signals are combined to form a composite signal. So we are forming some kind of composite signal, and that composite signal is again demultiplexed at the other end by suitable technique. Now, how FDM is implemented? In implementation, first we divide the available bandwidth of a single physical medium into a number of small independent frequency channels, and using modulation, independent message signals are translated into different frequency bands, and all the modulated signals are combined into a linear summing circuit to form a composite signal. So this is composite signal we are going to form from this uh, TDM system. And composite signal, it is for the transmission through the medium which has a higher bandwidth. The carriers used to modulate the individual message signals, these carriers are known as the subcarriers. So here we are not using a single frequency carrier, but a number of frequency carriers are used. Different carriers are used for the different sources. And after the modulation, we are combining and then sending through the transmission medium. And if we talk about the transmission bandwidth, you can see if this is the frequency of signal first, and this is frequency f2 of signal second, and frequency fm of signal m. Then we can say when guard band is not provided in between these signals, there is no guard band, then you can say the bandwidth will be n into fm. And here, if for each xt has the same bandwidth fm, so if each signals having the same bandwidth fm, this is centered frequency f1, centered frequency f2, centered frequency f3, but the bandwidth is fm for all the signal. So then the total transmission bandwidth, it will be n into fm, where n is the number of message signals or number of sources. And if all the xt's are having different frequencies, just like fm1, fm2, fmn, then we can say the bandwidth will be f1 plus fm2 plus fmn. So this is the transmission bandwidth of the FDM system. Now, when the guard band is used between these two signal spectrum, so if the signal bandwidth is fm and the guard band bandwidth, if it is fg, then the total transmission bandwidth, the total number of guard band between n channels, it will be n minus 1. So the total transmission bandwidth, it will be n fm plus n minus 1 fg, where fg is the guard band frequency. And at the receiver, the different signals f1, f2, fn are received, and with the help of a demodulator, with the carrier frequency f1, f2 to fn, they are separated out in f1 to fn. So here we get different frequency bands. They are filtered out and they are then sent to the different destinations. Here we have used guard band so that the channels are separated by a strip of unused bandwidth to prevent interchannel interference, or if the channels are very close, then the signals of one channel will disturb the signal of the other channel. So to avoid this kind of thing, we have to use the guard bands between these bands. Now, advantages of FDM. In FDM system, users can be added to the system by simply adding another pair of a transmitter, modulator and a receiver demodulator. And FDM system supports full duplex information flow, which is required by most of the applications. And noise problem for the analog communication has lesser offer. And also the FDM does not need synchronization between its transmitter and receiver for proper operation. And if we talk about the disadvantage in FDM system, the initial cost is high. In FDM system, a signal for one user can sometimes affect the others, that is intermodulation distortion takes place. And in FDM system, user requires a precise carrier frequency and a large number of modulator and filters will be required there, and the communication channel must have a very large bandwidth. Now if we talk about the applications of FDM, FDM has found application in our day-to-day life. The The transmission of AM FM radio broadcasting, that is with the help of radio receiver you can tune different channels. That means you can select different frequency and listen to the particular channel. Cable television, where usually coaxial cable 500 megahertz bandwidth, we can send as many as 100 different channels and they can separate out with the help of band pass filter at the receiver. And in telephone system we use FDM, and the first generation of cellular phones have used the FDM. Now we will discuss about wavelength division multiplexing, WDM. It is commonly used in case of optical fiber. It is somewhat similar to FDM but at the higher frequencies. We normally refer to frequency division multiplexing as wavelength division multiplexing because the wavelength values is smaller. So for the higher frequency values, FDM is usually referred to as WDM. So WDM is conceptually same as the FDM, except that the multiplexing and demultiplexing involve optical signal transmitted through the optical fiber channel. And now application of WDM, potential application of WDM is in the fiber to the home, fiber to the curb, fiber to the office, and all these type of systems. And one important application of WDM is the SONET network, in which multiple optical fiber line are multiplexed and demultiplexed. Now we come to the digital multiplexing. It is two types: synchronous time division multiplexing and asynchronous time division multiplexing. First we will discuss synchronous time division multiplexing. In FDM, all signals operate at the same time with different frequencies, but in TDM, all signals operate with the same frequency but at different times. So in TDM, all signals are not sent simultaneously. Instead, they are transmitted one by one. The incoming data from each source are buffered. Each buffer is typically 1 bit or 1 character in length. The buffered are scanned sequentially to form a composite data stream. So here we can see this is for n time slots. So for every users there is one time slots, and they make a one complete frame. And the composite signal can be transmitted directly through the modem. And how the other side, that is receiving end, identify that this is the beginning of the frame. For this purpose we use extra pulses for synchronization, and these data pulses along with the control information form a frame. And in synchronous TDM, each time slot is pre-assigned to fixed sources. The time slots are transmitted irrespective of whether the sources have any data to send or not. Here, for the sake of simplicity of implementation, channel capacity is wasted. For example, if there are n sources, when a signal frame consists of n time slots, and each time slot is dedicated to exactly one source for carrying data from the corresponding input. Each source plays its data to the link only when the corresponding slot arrives. In synchronous TDM, if a device does not have a data to send, then its time slot remains constant. Both multiplexing and demultiplexing operation for synchronous TDM. So here you can see, if we are having n sources, so this TDM system scan one by one from S1 to Sn, and for a fixed time there is a scanning for a fixed time for S1 to S2, and in the during the scan time S1 transmit their bit, and similarly S2 to Sn. So this is a frame, and this include extra pulses or bits for synchronization or control data information, and this frame then transmitted. And if and if you can see, if there is no data for the for any source to transmit, then the frame will be empty. You can see here in this figure that there are one, two, three, four sources, and source one having data to transmit a, and B's, and second having B, 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 and third having C, C, and fourth is D. So it is going to scan one by one from this. It collect A, and from second it collects B, and from third it collects C, and from fourth it collect D. Will make combinedly first frame, and after the second scan, this system collect A from first, B from second, C from third, and from fourth there is no data to send because D is already transmitted. So this block is empty here. And also in the next scan, A is selected from first, B is selected from second, there is no data and there is no data. So these are empty, and these remains empty because there is no data. And at the receiving end, similarly, these will be empty, these boxes will be empty because these time slots empty because there is no data. So there is a there is a wastage of capacity of the system. So this is the disadvantage of synchronous TDM. So about the disadvantage, the channel capacity cannot be fully utilized when some sources do not want to send the data, and the capacity of the transmission link must be higher than the total capacity of the input link, and it is very complex to implement. Now we will discuss about asynchronous TDM. In synchronous TDM, if a particular terminal has no data to transmit at a particular time period, then corresponding slot in a frame is wasted, or an empty slot will be transmitted. Asynchronous TDM or statistical TDM is used to overcome this. It dynamically allocates the time slots on the demand to separate input channels. So, saving the channel capacity here, the time slots are flexible and total capacity of the input link can be greater than the link capacity of the channel. And in synchronous TDM, if there are n input lines, there must be n slots. But in asynchronous TDM, if we have n input lines, and then the frame may contain less than n slots. And you can see here the same question, and you can see the first frame having 4 time slots, second frame having only 3 time slots, and third frame having only 2 time slots. So based on the available data, the time slots will be varying, the length of the time slots is varied. So here the number of slots in a frame is based on the statistical analysis of the number of input lines and the transmission of data with asynchronous TDM. You can see in this figure. Now, if we talk about the advantages, TDM uses a single link, and TDM does not receive precise carrier matching at both the ends of the link, and full available channel bandwidth can be utilized for each signal, and there is no intermodulation distortion, no crosstalk, and in TDM circuitry is not very complex. Now we will discuss about disadvantages of TDM system. In TDM system, synchronization is essential for proper operation, and initial cost is high, and technical complexity is more in TDM system. Now, digital signal DS service. The telephone companies implement TDM through the hierarchy of digital signals, and this is known as the digital signal services or digital hierarchy. And in this figure, you can see the digital hierarchy. The DS digital signal 0, DS0. A DS0 signal is the basic input signal, which is a single digital channel using 64 kbps PCM channels. And DS1, 24 DS note signals are multiplexed using TDM to produce a DS1 signal, and the bit rate of DS1 is, you can say, 24 into 64, or you can say 1.544 mbps, and also there may be 8 kbps of overheads, and 4 such DS1 signals are multiplexed at the second level of multiplexing to obtain DS2 signals, and has bitrate of 6.312 mbps. Now, 7 DS2 signals are multiplexed to produce DS1 signal, and its bitrate will be 44.376 Mbps. And finally, 6 DS3 lines are multiplexed to obtain DS4 signal, and its bitrate is 274.176 Mbps. And here DS note, DS1, DS2, etc. are the names of the services, and the telephone companies use the T line, T note, T1, T2, etc. for to implement these services: DS note, DS1, DS2. And this table shows the relation between the DS service and T lines. DS1 service indicates the line T1, and bitrate in Mbps it is 1.544, and number of voice channels are 24. And DS2, it is DS2 service is implemented using T2 line, and the bitrate is 6.312, and the number of voice channels are 96. And DS3 service can be implemented using line T3, and the rate it is Mbps in 44.736, and the number of voice channels are 672. And DS4 is implemented using T4 line, and the rate in Mbps it is 274.176, and the number of voice channel is 4032. So T1 lines implement T1 services, T2 implements S2 services, and so on. S note is defined as the basic service. The T lines are the digital lines which are designed to carrying a digital data, audio or video. But the T line can also be used for analog communication, that is, T1 line can be used for the telephone applications. Now, PCM TDM system, T1 lines, T1 system. When a large number of PCM signals are to be transmitted over a common channel, multiplexing of these PCM signals is required. This figure shows the basic TDM schemes for the PCM voice channels, and this is known as T1 digital system. And here you can see there are 24 voice channels, and they are combined, and before the combination we will use the pulse code modulation, and it will use 64 kbps. So there are 64 kbps lines, and they are TDM multiplex, and the T1 lines make the rate 1.544 mbps. And here there is extra 8 kbps overhead there for the synchronization purpose, and this system is used to convey a number of voice signals over telephone lines using wideband coaxial cables. Now, comparison of FDM and TDM system. In FDM, the signals which are to be multiplexed are added in the time domain, but they occupy different slots in the frequency domain. And in TDM, the signals which are to be multiplexed can occupy the entire bandwidth, but they are isolated in the time domain. And in FDM is usually preferred for the analog signals, and TDM is preferred for the digital signals. And in FDM, synchronization is not required, but in TDM, synchronization is required. And in FDM, the FDM requires a complex circuitry at the transmitter and receiver, and TDM circuitry is not very complex. And FDM suffers from the problem of crosstalk due to the imperfect band pass filter, and in TDM the problem of crosstalk is not solved. And due to wideband fading in the transmission medium, all the FDM signals are affected, and due to fading only a few TDM channels will be affected. And due to slow narrowband fading takes place in the transmission channel, only a single channel may be affected, and in TDM, due to slow narrowband fading, all the TDM channels may get affected. Now, the comparison between FDM, synchronous TDM, and asynchronous TDM system. And the parameter for the comparison is, if we consider the parameters, line utilization efficiency. The line utilization efficiency in FDM is poor, and in synchronous TDM it is good, and in asynchronous TDM the line utilization efficiency is very good. And if we talk about the flexibility, FDM are poor, but synchronous TDM is good in the flexibility point of view, and asynchronous TDM is very good on the point of flexibility. And if we discuss about the channel capacity, the FDM having poor channel capacity, synchronous TDM having good channel capacity, and asynchronous TDM having the excellent channel capacity. And error control point of view, uh, in FDM and synchronous TDM there is no possibility of error control, but in synchronous TDM there is a possibility of error controlling. And multi drop capacity, and in FDM it is very good, but in synchronous TDM it difficult to achieve, and in asynchronous TDM it is possible to have multi drop capacity. And if we talk about the transmission delay, FDM does not exist the transmission delay, and in synchronous TDM there is low transmission delay, and in asynchronous TDM there is random transmission delay. And if we talk about the point of view of cost, in FDM the cost is high, and in synchronous TDM cost is low, and in asynchronous TDM there is moderate cost. So this is the end of this lecture. Here we have discussed about different types of multiplexing, that is FDM TDM, and this was 24th lecture of the lecture series of Basics of Communication Engineering. In this lecture we have discussed about analog modulation. In the next lecture we will discuss about digital modulation. Till then, thanks for listening this lecture. Thank you.